Hi, hello. Our topic for today is about bandwidth and noise. Okay, so bandwidth and noise are two major or important considerations when we are talking about communications. Either it is an analog communications or a digital communications. Bandwidth and noise are the two very important topics about it. Okay, so let's start with the electromagnetic spectrum. Okay, so signal before we can transmit your signals into longer places or distances, we should convert them first into electromagnetic waves. So what are electromagnetic waves? So these are signals that tends to oscillate. Okay, so we have a term here, electromagnetic spectrum. So electromagnetic spectrum is the entire range of frequencies. So many applications, different applications in communications, they are divided into into the electromagnetic frequency spectrum depending on what are their frequencies. Okay, so for example, we are going to talk about AM communication. So AM has a place or a definite location in the electromagnetic spectrum. Okay, so it's a specific frequency or bandwidth. Okay, so if you are if you are an engineer in that specific field of communication, for example, AM broadcasting company, so you will be designing electronic circuits such as oscillators, such as filters that will function at that specific frequency range. Okay, so those range of frequencies, we can find them in an electromagnetic spectrum. Okay, so when we say frequency, this is the number of times a particular phenomenon occurs in a given period of time. So the unit for frequency is cycles per second, but we are more familiar with its unit in terms of hertz. Okay, so one complete cycle, um, if we have one complete cycle, we have each alteration or oscillation. So when we say one complete cycle, we are talking about one complete alteration of a waveform. So we have a positive half cycle and a negative half cycle. So one positive and one negative, this consists a cycle or a complete waveform. Okay, one cycle per second is equivalent to 1 hertz. 1 hertz. So we can specify frequency as cycles per second, although we are more familiar, or we mostly use the unit or the unit as hertz. Okay, so we have here, this is your one complete cycle. Okay, so usually we make use of a sine wave. And then we have here another term, which is wavelength. So wavelength is the distance between 2 points of similar cycles of a periodic wave. So for example, we have here a positive half. One wavelength is from the start of this positive half to the start of the next positive half cycle, or from the start of the first negative half to the start of the second negative half. Okay, so the positive half, we call this a short crest, while the negative peak here, we call this a short throw. Okay, so this is the distance traveled by an electromagnetic wave during the time. So that is your wavelength. So we have here the relationship of frequency and wavelength. Okay, so this is our symbol for wavelength, which is lambda, and that is equivalent to c, which is your velocity of light, divide by your frequency. Okay, so most of the time we use the unit meter per second, or that is 300 million or 300 times 10 raised to 6 meter per second, divide by the frequency. Or we can also make use of inches per second or feet. So it depends on what unit of configuration. So one type of problems that may occur here is the formula is very simple, but you may ask to solve for a wavelength given different units. Okay, so this can be in terms of English measurement, English system, or metric system. Like for example, meters per second, it's in the meters metric system, and then inches per second, it's in the English system. So this is where your knowledge in conversion will come to place. Okay. So, your wavelength is inversely proportional with the frequency. So, what do we mean by that? If you have high frequency, the shorter your wavelength is, but the lower your frequency is, the longer your wavelength is. Okay, so these are the different divisions or the different parts of your electromagnetic spectrum. Okay, so we will be starting from the extremely low frequency. Okay, and then we're going to up to extremely high frequency range. Okay, so it is from 30 to 300 kilohertz. So what is the important application that we are very familiar that will fall under this category? So that is your AC power lines. So if you will be remembering, your AC power line is 60 hertz. So therefore, it is under this category. And then, this is your voice frequency. Okay, so this is where our voice, human voice frequency falls into. So this is from 300 to 3000 hertz or 300 to 3 kilohertz. Okay, so the voice frequency is equivalent to 20 to 20 kilohertz. So it falls here. Okay, so from 20 to 20 kilohertz. Okay, so we have here a very low frequency. So this is where some musical instruments or navy communication takes into place. So we have here low frequency. So this is where aeronautics and marine navigation in falls into place. So therefore, in their airplanes or in their ships. Okay, so the frequency that they're using is mostly falls between this frequency range. Okay, and then we have here the medium frequency range. So the medium frequency range is 300 to 3 megahertz. This is one important or one popular application under this is our AM broadcasting. So AM broadcasting is 535 to 1605 kilohertz. So this falls under the medium frequency range. Okay, and then we have here the HF or high frequency. So we have here your amateur radio or your citizens band radio. Okay, so when you're riding on a van and then the driver wants to communicate with the other drivers, okay, so they make use of this frequency. That means their transmitters and receivers are designed in this frequency range. Okay, so the frequency that they're transmitting and the frequency that they're receiving falls under this frequency range. Okay, and then we have the VHF. Actually, digital analog broadcasting falls between VHF and UHF. So we have here the low channels. Okay, so from channel 2 to channel 13, they fall within this category. So we have the VHF, and then higher channels from channel 14 upwards, so they fall under UHF. Okay, and also we have here your FM broadcasting. Your FM broadcasting is from 88 to 108 megahertz. So it is under your VHF. Okay, then we have here satellite communications and radar. Under the super high frequency range, and then the extremely high frequency range, we have also satellite communication and specialized radar. Okay, so these are the summary this is the summary of your electromagnetic spectrum with its popular application. Although there are more, okay, popular application like telephone communication, we have digital communications, we have microwave communication. So they fall under one of this range. Okay, so the electromagnetic spectrum, this is the range of electromagnetic signals encompassing all frequencies. So it is referred as the electromagnetic spectrum. Okay, so we can visualize the electromagnetic spectrum like this. Okay, so we have here the name, and its corresponding wavelength. So as you can see, the lower the frequency, the higher the wavelength. So as the frequency increases, likewise your wavelength decreases. Okay. So we have here some examples, although we have already discussed or mentioned this a while ago. So we have here extremely low frequency. This also includes the lower end of the human hearing range. As I've mentioned, human voice is hearing is also from 20 to 20 kilohertz. Okay, so we have here low frequency, that is the human hearing range, so 20 hertz, so it falls under here. And then we have here the low frequency telemetry signals. Okay, so when you want to send measurements to space, so we use this frequency range. Okay, and then human speech falls under this. And since what is being used in telephone channels or standard telephone channels are voice, so standard telephone channels also falls under this range. So, very low frequency, higher end of human hearing range. Okay, so some musical instruments, they have this frequency range. And then we have the specialized government and military systems. Okay, for submarine communications, they make use of this frequency range. So that means whatever they are transmitting and receiving information, whenever they are transmitting and receiving information in their submarine communication, the design of their electronic circuits, the frequency is under within this specific range. Okay, so low frequency range, marine and aeronautical navigations or subcarriers. Okay, so medium frequencies, so AM radio, so it says there 535 to 1605 kilohertz, and other marine and aeronautical communications applications. Okay, high frequencies, we call this short waves. So this is where your two-way radio communications or short-wave radio broadcasting, the amateur radios, the citizens band communications, Voice of America and Radio Free Europe broadcasting. So they fall under high frequency. Okay, so very high frequency mobile radio. Okay, so your smartphone, okay, so it's either Globe or Smart, whatever your carrier is. So you have here your marine and aeronautical. So the commercial FM, so this is 88 to 108 megahertz. Commercial TV broadcasting, we're talking about analog commercial TV broadcasting. So from channels 2 to 13, so that is from 56 to 216 megahertz. So channel 14 and above, we are in the ultra high frequencies. Okay, so this is channel 14 to channel 83. Okay, so you have the land mobile communications and services, radar and navigation services for military purposes, microwave and satellite radio systems, and microwaves. Okay, so they fall under the ultra high frequency. So we have here the super high frequency microwave and satellite communications or radar. Okay, so extremely high frequency, very sophisticated, expensive, and specialized applications of radio communications. So in this case, we are using millimeter waves. So the wavelength here are very, very small, very, very short waveforms because of the high frequency. We have here infrared. Okay, so 3 to 30 terahertz, okay? So not they are not considered radio waves anymore. Okay? So what we're going to consider here in analog communications are radio waves. Okay? Beyond that, in infrared upwards, they are no longer considered as radio waves. Okay, so infrared signals, they are electromagnetic radiations generally associated with heat. Okay, say they used in heat seeking guidance systems, electronic photography, and astronomy. So the infrared region is sandwiched between the highest radio frequency and the visible portion of the electromagnetic spectrum. So we have here some uh, values that are very important that you may encounter in your future subjects or questions that you may encounter when you have your pre-boards. Okay, so 1 micron is equivalent to 1 millionth of a meter. So we have here long infrared, so 0.01 millimeter to 1000 nanometer. So they are very, very short waves, okay, wavelengths. So short infrared 1000 to 700 nanometer. So usually their applications are under astronomy, guidance and weapon system, TV remote control units. Okay, so we are not going to deal on this further because our more concern is on the AM and FM broadcasting. Okay, so we have here visible light. So these are the visible range for humans. Okay, so we have here light wave communications. So light is a special type of electromagnetic radiation that has wavelength in the zero point 0.4 to zero point 0.8 micrometer range. Okay, so your light wavelength is usually expressed in angstrom. Okay, 1 angstrom is equivalent to 1/10,000 of a micron. So the visible range is from 8,000 angstrom, or we can say 4,000 angstrom to 8,000 angstrom. Okay? So however, maybe in your future electronic communication subjects, but in analog communications, we will not be dealing on this. But you just have to be aware of the values, of the definitions, of the terms that you may encounter someday. Okay, so we have here lasers. They operate on extremely narrow beam of light, which is easily modulated with voice, okay, video, and data information. Okay, so ultraviolet rays, you have 3 to 30 pesohertz. So X-rays, you have gamma rays, and you have cosmic rays. So this is beyond your radio waves communications, okay? This is about classification of transmitters, but I think we're not going to deal on much of this. But you still have to have an idea regarding this. Okay, so classification of transmitters. This is for licensing purposes in the U.S. Okay, but we also adapt it here. And sometimes some questions from you might encounter when you have your pre-board subject or even the board exam, some questions are still about these classifications of transmitters. Okay, so they are being identified by a three-symbol code containing a combination of letters and numbers. Okay, so what are those codes? First is what are the types of modulation of the main carrier? So is it amplitude modulation? Is it frequency modulation? Is it phase modulation, or even digital broadcasting? Okay, so is it frequency shift keying, phase shift keying, etc. So the type of modulation of the main carrier is specified by a letter. Okay, so identifies the type of emission. So the type of emission is represented by a number and describes a type of information. It also is being specified by a letter. Okay, so for example, we have A3E. Okay, what does an A3E stands for? Okay, so M Okay, so the first letter stands for modulation type. So we have A for AM, H for single sideband. So there are different types of AM that we're going to discuss in the future. So we have here AM single sideband full carrier. So you have AM single sideband reduced or controlled carrier. J, you have AM single sideband suppressed carrier. You have B, AM independent sidebands. C, you have AM vestigial sidebands. So this type of AM, we're going to define that in the future. Okay, so our example earlier is A3E. So A, that means you are the type of modulation that you are used is the standard AM. So what do we mean by standard AM? Standard AM is your double sideband with full carrier. Okay? And then we have here for FM. So these are the different types, and even pulse amplitude modulation, pulse width modulation. So this is for digital communications already. Okay? And then we have here some. So these are the letters that you can use in the first letter of your code. Okay? And then for the number, okay, so this is the nature of modulation. Okay, so in our example A3E, we have number 3. So what does number 3 stands for? It is a single analog channel. So you are just transmitting a single analog channel. And these are the other numbers that you can make use of. Okay, and then the third letter is the information type. Okay, so in our example, we have here A3E. So E stands for telephony, voice, or sound broadcasting. So therefore, we are trying to transmit audio. Okay, so voice, because since it is an AM, so maybe it's voice, and we are having your, or we are transmitting using your sound broadcasting. Okay, so that's an example of your 3-digit codes. So this is just an example. Okay, so again, you have here the higher end of the human hearing range is 20 kilohertz. Okay, so we have this a while ago. So I have to skip up to this now. So we have here your FM broadcasting and your channels 2 to 3, channels 14 to 67, and your cellular phones under ultra high frequency range. Okay, and then you have there those examples. So the optical spectrum, it exists directly above the millimeter wave region. So millimeter, that means your wavelength is in terms of millimeter already. So there are 3 types of light waves. You have the infrared, we have the visible spectrum, and you have the ultraviolet. Okay, so this time we will be starting with our main concern, which is bandwidth. Okay, so bandwidth is one important concern in our communication. Okay, so the amount of information that you can send, okay, or the amount of information that you can receive is highly dependent on the bandwidth you are using. Okay, so how fast or how slow you are going to transmit or you receive your information, it is dependent on your bandwidth. Okay, so basically speaking, or defining bandwidth, so bandwidth is that portion of the electromagnetic spectrum which is occupied by your signal. Okay, so for example, we are going to transmit an AM signal. So what is the bandwidth for an AM signal? Okay, so you have to design a transmitter that is capable of transmitting this specific bandwidth, because in this specific signal range, this is where your signal, okay, this is what we're going to, this is the bandwidth of the signal that you're going to transmit. So the channel bandwidth refers to the range of frequencies required to transmit the desired information. So if you are working on an AM station, what must be your channel bandwidth, okay, so that we can transmit that required information. Okay, so there are more room at the top. So what do we mean by that? So today, virtually the entire frequency spectrum between approximately 30 kilohertz and 300 megahertz has been spoken for. So majority of what we are using, majority of what we are implementing, or what we know lies between this 30 to 300 megahertz. Okay, so there is tremendous competition for these frequencies. Okay, so before, Globe only has the frequency of 0917, but because of many subscriptions, okay, so so they have additional, they requested for additional frequency. Let's say, so Globe, instead of 0917, they have already 0916. Okay, or Smart, before, they only use the frequency spectrum of 0918, but now they also have 0919, and so on. Okay, so there are lots of, when you have lots of subscriptions, the tendency is that your bandwidth maybe you stop. Okay, so it will be, what do you call this, saturated. So you need more space, you need more bandwidth. Okay, so there is tremendous competition for these frequencies between companies, individuals, and government services, in individual carriers, and in between the different nations of the world. So since we are now in the pandemic, and we have here using work from home, online classes, and everything. So even at the comfort of your home, you are experiencing this competition, okay, in frequencies. Okay, for example, even though you have a good quality internet at home, and yet you are using several devices, how many are you using that specific bandwidth? So we can still experience this competition. Okay, so the electromagnetic spectrum is one of our most precious natural resources. So our main goal is, how are we going to maximize this? Okay, anyway, how are we going to make use of this effectively, efficiently? So communication engineering is devoted to making the best use of that finite spectrum. So you see, it is not infinite. It is finite. So what do we mean by finite? It has its ending. Okay? It has its limitations. Okay? Because when we say infinite, it has no limitations. But sadly, our bandwidth is finite. So therefore, we just have to make use, okay? We just have to maximize of what we have. So great effort goes into the developing communication techniques that minimize the bandwidth required to transmit given information, and thus conserve spectrum space. Even since you are online, we are online, okay? So you are required to submit, you're required to submit researches, you're required to submit assignments and everything. So we have several techniques, and as simple as our example is that, how can you send an email that is very, very large? For example, it has lots of pictures in it, it has programs and informations in it. So it's very, very, it has a very, very high capacity. So we usually zip it. Okay, so we usually zip it before sending it. So that is one way, okay? So for example, pictures, we compress it, okay? Because if we do not do those techniques, it will be very difficult for us to send information. So like that, okay? So this provides more room for additional communication channels, and gives other services or other users an opportunity to take advantage of it. So for example, TV stations, for channels 14 to 83, for example, some of those channels are unused for TV broadcasting. So how do we maximize it? So sometimes, okay, telephone companies just get frequencies from there, borrow frequencies for them. Since it is not being used for TV broadcasting, can we use it for telephony? Can we use it for cellular telephone instead, so that it will not be left unused? Okay, so we have to take advantage of those things. Okay? So, spectrum management is provided by agencies set up by the United States and other countries to control the spectrum use. So, in the US, okay, so the Federal Communications Commission or your FCC and the National Telecommunications Information Administration, NTIA, are two agencies that deal in spectrum management. So in here in the Philippines, so we have also our National Telecommunications Commissions or the NTC. Okay, so they manage the spectrum. So they allow, okay, a company, they allow an entity to make use of this specific bandwidth for their application, for their purposes. Okay, for example, I will be giving this frequency to ABS-CBN. I will be giving this frequency to okay, but it's not there. So it's just for a certain period of time, okay? And they also have the power to take it off if there is some irregularities or if the contract expires, just like what happened recently to ABS-CBN. Okay? So, to have spectrum management, they have to set certain standards. Okay? So, standards or specifications and guidelines necessary to ensure compatibility between the transmitting and receiving equipment. So, since, for example, you are going to transmit this specific frequency, so your transmitter must be designed in transmitting this frequency only, because if your transmitter has other frequencies on it, you might interfere with other channels, with other stations, with other applications. So definitely we have to follow certain standards. So your designs will have to be following those standards that are allotted to you. Okay, so bandwidth and information capacity. So the significant limitation on the performance of any communication system, either it is analog or digital, we have two. Okay, so we have bandwidth and we have noise. So bandwidth is that portion of the electromagnetic spectrum that is occupied by a signal. Okay? So the frequency range over which an information signal is transmitted, over which a receiver or other circuit operates. So the difference between the upper and the lower frequency limits of the signal or the equipment operation range. So the channel bandwidth is given by the range of frequencies required to transmit the desired information. So we have here your bandwidth is equivalent to your upper frequency range minus, okay, your lower frequency range. Okay, so some other books, some other references, they make use of this as FH, stands for higher frequency, and this is FL, which stands for lower frequency. Okay? So the totality of this will be your bandwidth. Okay, so we have here information theory. So this is the bandwidth of your channel capacity must be greater than or equal to the bandwidth of the information. Okay, so the bandwidth of your channel capacity must be greater than your information, because it will be carrying your information. So what will happen if if your channel is lower than your information, so it will not be possible. Okay, so information theory is a highly theoretical study of the efficient use of bandwidth to propagate information through electronic communication systems. Okay, so it also deals with information capacity. So this is a measure of how much information can be transferred through a communication system in a given period of time. So we have here your Heartless Law. Okay, so this is from R. Hartley in 1920 from the Bell Laboratories. It says the wider the bandwidth and the longer the time of transmission, the more information that be conveyed through the system. So the information capacity is directly proportional to the bandwidth and to the time. So for example, you are uploading a file, or if you are downloading a file, okay, so the higher, or the higher your information capacity is, okay, so the longer it will take for you to upload or download your file, okay, and higher the bandwidth you have, the faster or the slower your information capacity will be uploaded or downloaded. Okay? So your B stands for your signal bandwidth and your T is your transmit time. So another information theory is from C. Chad Shannon in 1948, okay, also at Bell Telephone Laboratories. So this relates information capacity, bandwidth, and noise. Okay, so if you're going to go back here, noise is not included. So technically, this is such as an ideal condition. Why? Because we didn't take into consideration the effect of your noise. But in reality, class, okay, in reality, noise is there because once you transmit your information and it passes through your medium, noise tends to be included in your signal. Okay, so in this information theory of Claude Shannon, he relates the information capacity, the bandwidth, and the noise in a form of a signal to noise ratio. Okay, so in his analysis, he has here the formula I, which is your information capacity in bits per second, okay, is equivalent to B, which is the bandwidth, logarithm to the base 2 of 1 plus signal to noise ratio. Okay, so your signal to noise ratio is unitless because we are considering the noise, the power of your signal, divided by the power of your noise. Okay, so this is a unitless system. However, we are in our calculators, okay, in our usual computations, we make use of either two logarithms. Okay, so we make use of the natural logarithms, which is your ln in your calculator, and we use the common logarithm, which is in the base 10. Okay, so to relate this logarithm to the base 2 and logarithm to the base 10, okay, we have here a constant which is 3.32. So this 3.32 is from converting your base 2 to base 10. Okay, so uh, we can solve for the information capacity, and it is directly proportional again to bandwidth and your signal to noise ratio. Okay, or we can solve for your bandwidth just by dividing this information capacity by logarithm to the base 2 of 1 plus signal to noise ratio. Okay, so let's have an example here for a standard voice band communication channel with a signal to noise power ratio of 1000. Okay, so later we will be discussing how did 1000 became 30 decibel. Okay, so we have here your signal to noise power ratio can be in a form of your unitless value, or we can express this in terms of decibels. In communication systems or in data sheets, usually they are given in terms of decibels. Okay, and a bandwidth of 2.7 kilohertz. The information that can be transferred is just following the formula. Okay, so we have here 26.9 kbps. Okay, so if you do not know how to use your logarithm to the base 2 using your calculator, you just make use of the 3.32, okay, multiplied by 2,700, then logarithm of 1 point plus 100. So you can get the same answer. Okay? So that is in terms of kilobits per second. Okay, so that is the information that is being transferred in a standard voice band communication. So here we have here decibels. Okay, so what do we mean by decibels? So when do we use decibels? We usually use decibels when we are dealing with large and small signal levels. Okay, so your decibels are in powers of 10. Okay, so we have here your decibel in terms of power. Okay, so your P2 all over P1, this is your absolute power. This corresponds to your output power and your input power. Okay, so this is your power gain. Okay, so this is your power gain or power, it can either be a gain or a loss. Okay, so it's a gain when your numerator is greater than your denominator. That means the output is greater than your input, and it's a loss when your output is lower than your input. Okay, so for power, we use 10 logarithm. So later on, we're going to encounter voltage gains. We're going to encounter current gains. Okay, so we will just be relating your voltage to power and your current to power. Therefore, we will be getting 20 here instead of 10. Okay, so we have here your power in terms of decibels. Okay, in terms of watts, if we have here your unit as watts. Okay, and it is dBm. Okay, so the small letter m there stands for milli. Okay, so when do we use milli? We use when our unit is in terms of milliwatts, or our reference is in terms of milliwatts. Okay? So you can also encounter some which is dB micro. So what do we mean by micro? So that your reference power this time is in terms of microwatts. Okay. So dB is a ratio, okay, but this is your power ratio, okay? So we just convert that into decibel. So your power ratio is unitless. Once converted into decibel, it already has a unit which is dB. Okay, so it will become dB watt. So this is an absolute value in watts. That means the reference that you are using is equivalent to 1 watt. dBm, this is also an absolute value in milliwatts. That means the reference that you are using in your denominator is 1 milliwatt. Okay, so you can add dB watts to dB to get a new value in terms of dB watts. Okay, so your output dB watt is equivalent to input dB watt plus your gain. So we can simply add them. Okay, so multiply absolute values. So if you want to get the output power and the decibel is given, all you have to do is to multiply your input with the gain. So that will give you your absolute values. So absolute power using decibels, okay? So if you have dBm, your reference is 1 milliwatt. When your input is equal to your output, that means you don't have gain nor loss, okay? That is equivalent to 0 dB. Okay, so 0 dB means that your output is just equal to your input. So we have here, if our reference is 1 watt, okay, so we have here 10 divided by 1 watt, so that will give you 9 dB watts. Okay, so always remember that every time it doubles, you just have to add plus 3 dB. Or every time it is halved, you have to subtract 3 dB. So that is for absolute power. Okay, so powers greater than 1 watt. So that will give you 4 dB watt. So that is 1 watt. So this is, when you double it, that is 2. So that is 3 dB. So when you double it again, so that will give you 4. So that will give you 6 dB. You double it again, that will give you 8. So that will give you 9 dB. So what do we mean by that? Every time you double this one, you multiply it by 2, okay? So you will have an additional or a decrease Okay, for example, you make this 1/2. So that will give you negative 3 dB. Okay, so dB watts. So in terms of wattage, so as you can see, 10 megawatts. So 10 megawatts, if you're going to write this in its absolute form, it's very, very long. So many zeros. But if you're going to write this in decibels, that is just equivalent to 100 dB watts. Okay, so decibels will help us in writing longer, okay, numbers, either in positive or negative engineering notations. So power which are lesser than 1 watt. So you have this one, you have again, half again. So that will give you minus 3 dB each cases. Okay? So how about if you multiply it by 10? Okay, so per decade. So that will give you naman an additional or a decrease of 10 dB. In this case, if you multiply it by 10, you have an additional so 10, multiply it again. So 20, so multiples of 10. So that will give you what? One additional dB power. Okay, so we have here a technique. You just what do you call this, count the number of zeros, then multiply it by 10. So for example, this is 0. Okay, so how many zeros do you have? 1. So times 10, you have 10. How many zeros do you have? So you have 2. Okay, so you multiply it by 10. After multiplying this by 10, you are adding 10 dBs in terms of decibels. So how many zeros do you have here? You have 2 times 10, you have 20 dB. How many zeros do you have here? You have 3. Okay, so times 10, 30 dB. How many zeros do you have here? Okay, so that is 10 zeros. So 10 times 10, you have an equivalent of 100 dB watts. Okay, so same is true. So the only difference is we have a negative sign here. Okay? So a positive dB means gain, while a negative dB signifies loss. Okay? Or the output is lesser than your input. Okay, so those are about bandwidths. Okay, so the next important consideration in communication, of course, are noise. Okay, so we have several types of noise. Okay, first we have an electrical noise. Okay, so electrical noise, any undesirable, we don't want noise. Okay, so therefore we design electronic circuits that are capable of eliminating this noises. Okay, so electrical noise, any undesirable electrical energy that falls within the passband of the signal. So your information is in the form of a bandwidth. It has a bandwidth. Once the frequency of that noise is within that specific bandwidth, therefore, your noise is already included in your signal. Okay, so we don't want that. Okay, because originally, the information that you sent doesn't contain any noise. Okay, so there are two types of noise. Okay, so you have what we call correlated and uncorrelated noise. So what's the difference? Correlated noise, they exist only when signal is present. Without your information, therefore, you have no correlated noise. Okay, so uncorrelated noise, on the other half, is this is always present whether you have a signal or not. Okay, so that means it is this type of noise is there. It's everywhere. Okay, so once you had your signals and that uncorrelated noise happens to fall within the passband of your signal, it can join, okay, or it can penetrate your signal. But your correlated noise, if you don't have your signal with you, therefore you don't produce correlated noise. Okay, so let us start first with the uncorrelated noise. Okay, so we have what we call external noise. Okay, so external noise, those are generated outside the device or the circuit. Okay, so there are several types of external noise. So one is your atmospheric noise, okay? So naturally occurring electrical disturbances that originates within the Earth's atmosphere. Okay, so it is mostly in a form of a static electricity. So sometimes, for example, you are just listening to your radio um, or having a conversation on the phone, and then suddenly you hear like that, a buzzing sound on your signal. So we can say that that is from your atmospheric noise. Okay, however, they become less severe at frequencies above 30 megahertz. Okay, but below 30 megahertz, we can experience your atmospheric noise. We have here your extraterrestrial noise. This consists of electrical signals that originates from outside Earth's atmosphere. Okay, so we also call this as the deep space noise. We have several definitions of noise. Actually, if you read some text, there are lots of noise, different types of noise. Okay, so maybe you just have to have an additional readings. Okay, if some of those types of noises are not included in our discussion. We have your solar noise. This is generated directly from the sun's heat. Okay, so we have what we call quiet condition when a relatively constant radiation exists, and high intensity. This is the sporadic disturbances caused by sunspot activity and solar flare-ups. Then we have cosmic noise. Sources are continuously distributed throughout the galaxies. Okay, so we also call this cosmic noise as galactic noise or black body noise. Okay, so if you happen to encounter questions like give some other names for cosmic noise. So cosmic noise are also called galactic noise and black body noise. So space noise are observable at frequencies in the range of 8 megahertz to somewhat above 1.43 gigahertz. Okay? So apart from man-made noise, it is the strongest component over the range of 20 megahertz to 120 megahertz. So we have your industrial noise. This is between the frequency of 1 to 600 megahertz. The intensity of noise made by humans easily outstrips that created by any other source, okay, either internal or external to the receiver. The nature of industrial noise is so variable that it's difficult to analyze it on any basis rather than statistical. Okay, so internal noise, this is an electrical interference generated within the device or the circuit. Okay, so we have here a shot noise. This is caused by the random arrival of carriers. Okay, so take note in electronics, we have two types of carriers. You have the electrons and your holes. Okay, and they are moving. They are constantly moving. Okay, so the we produce shot noise. They are caused by a random arrival of your carriers at the output element of your electronic device. So output element, for example, you have an amplifier. So usually we 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 uh we experience this at the collector side. So if you have FET, you experience that at the drain side, or at the output terminal of your device. Okay, so we also call this as your transistor noise. And then you have your transit time noise. Any modification to a stream of carriers as they pass from the input to the output of the device. So this happens when it takes the time it taken by an electron to travel from emitter to the collector. So emitter is your input and then collector is your output. Okay, of the transistor becomes significant. So there's a delay. Okay, in the period of the signal being amplified. Okay, so we experience some delay. So we call that transit time noise. So it goes on increasing with frequency at rate soon approaches 60 dB per octave. So when you double your frequency, just like what's our example earlier, when the power is 1, it became 2, it became 4, it became 8. So when you double your frequency, we call that class octave. Okay, so in power, it is 3 dB. But since we're talking about here output voltage, so that it became 6 dB. Okay, so why 6 dB? Because in decibel, when we're talking about voltages, it is no longer 10 log, it's already 20 logarithm. Okay, so when your absolute voltage or power increases by the power of 10 or decreases with the power of 10, we call it naman decade. Okay? So when you double or half your absolute voltage or power, you call it octave. When you multiply it by 10 or divide it by 10, you call it a decade. Then we have thermal noise, okay? So, of course, when you use your circuit, it has a tendency of increasing its temperature, okay? It tends to get hot. So, you have your thermal noise, okay? So, this is associated with the rapid and random movement of electrons within a conductor due to thermal agitation. Some other name for thermal noise, you have Brownian noise, you have Johnson noise, or white noise. Okay, so actually there are also a topic which are colors of noise. So if you have time, you can search on that topic. Okay, so this is a white noise. So there are different colors of noises. So the noise generated by a resistor is proportional to the absolute temperature in addition to being proportional to the bandwidth over which the noise is to be measured. So the noise power is directly proportional to the temperature and the bandwidth. Okay, so the larger the bandwidth, the more chances of your noise to enter your signal. And the higher the temperature, the noise power, the higher the chance of a noise power. So to remove this proportionality sign here and to replace it with an equality, okay, we have to introduce a constant, and that constant is your K. Okay? So now we have here your noise power is equivalent to KTB. Okay, wherein PN is your noise power in watts. Okay, B, that is your bandwidth in terms of hertz. K, that is your Boltzmann constant, and that is 1.38 times 10 raised to negative 23 joules per Kelvin. T is your absolute temperature, okay, in Kelvin. So at room temperature, every time we will be mentioning room temperature, we are talking about 27 degrees Celsius, okay? So that is equivalent to 300. So how do you convert your Celsius into Kelvin? All you have to do is to add 273. Okay? So usually in the problem we are given Celsius in temperature. So you just have to add 273 because in this formula we have to make use of Kelvin. Okay? So likewise, we can express your noise power. So this is your noise power in terms of watts. Okay? So the unit here is watts, but we can also express that in terms of decibels. Okay? So we usually make use of dBm. Again, what do we mean by dBm? When our reference value here is in terms of 1 milliwatt. Okay? So this is given by 10 logarithm to the base 10 of your KTB divide by 0.001 or 1 milliwatt. Okay? However, this we can express this bandwidth, okay, so since this is changing depending on what applications you are using, so we can also express your bandwidth in terms of decibel, so that is equivalent to 10 logarithm to the base 10 of your bandwidth. Okay. And then, we can make use of this KT since, for example, we are talking about room temperature. So, that is 27 degrees Celsius. And your K, your Boltzmann constant, is not varying. So, if you are talking about room temperature, we can safely make use of this formula. So, negative 174 dBm plus, depending on the value of the bandwidth. Okay. But if it is not in room temperature, we make use of this one if your T is not specified as room temperature. Okay? So, imagine yourself, what is your noise voltage? So, if you have a source, okay, so that source is, when we have a source, we always have an internal resistance for that source. Okay? So, if we have a noise voltage here, so it has a noise resistance here. So your it will be divided into two, considering they are equal. Okay, so only a portion will be going to your load, and that is your noise voltage. Okay, how do you compute for your noise voltage? So, assuming maximum power transfer, so remembering or recalling your circuit analysis. So, what is maximum power transfer? How can we attain maximum power transfer if we make use of equal resistances? Okay, so assuming maximum power transfer, your noise power is equivalent to your voltage squared divided by RL. Okay, so V squared all over R, assuming they are equal, R and RL are equal. So this is, your noise is just half. Okay, so assuming positive, they are, the noise source will be divided into two. So we have here Vn over 2 squared divided by R. So that will give you Vn squared all over 4R. In solving for your noise voltage now, that is equivalent to 4R multiplied by Pn. Okay, and then getting the getting the square root of both sides, that will give you 4k TB times R. Okay, so your KTB, your power formula here, which is your KTB, you just add 4 and R. So R is your resistance, noise resistance. Okay, so to solve for the noise voltage. Okay, so noise also has its own voltage value. So we have an example, an amplifier operating over a frequency range of 18 to 20 megahertz. So this is an operating range, okay? That means we can get your bandwidth here, has a 10 kilo ohms input resistor. What is the RMS? So automatically it's the RMS value. So what is the RMS noise voltage at the input of this amplifier if the ambient temperature is 27 degrees Celsius? Okay, so we have here the solution. We have the solution for that. Okay, so first, you need to solve for the bandwidth. So what is your bandwidth? Bandwidth is given by the higher frequency range minus the lower frequency range. So it is given by 20 megahertz minus 18 megahertz. So that will give you 2 megahertz. Okay, and the temperature is in terms of Celsius. So how do we convert it into Kelvin? So all you have to do is to add 273. Okay? So, substituting now in our formula, so the noise voltage is equivalent to 4K TB multiplied by R. So we have here your 4. K is your Boltzmann's constant. So you have that in your calculator already. So that is already stored in your calculators. So you have there 300, your temperature. You have here 2 megahertz. So you have to be very particular with the mega. Okay? So that means 2,000. 2 raised to 6. So 2 million. Okay? So 2 megahertz. And then our resistance is 10 kilo ohms. Okay, so we have a noise voltage which is equivalent to 18.2 microvolts. Okay, so what do we mean by that? It's very, very small. Okay, so we do not expect a high noise voltage. Why? Because we don't want noise voltage. So what we're expecting is the ideal value for noise voltage is 0. Okay, we don't want noise. So therefore, the smaller it is, the better. Okay, but again, it's not an ideal system. So we expect noise, but we expect a smaller value for noise. Okay. So we have another example here. Determine the noise power in watts. So this time we're asked to solve for the noise power in watts and in dBm. Okay, for an amplifier operating at a temperature of 400 degrees Celsius with a 1 megahertz bandwidth. So in this type of example, bandwidth is already given. We are not given the range, so therefore no need to subtract. This is already your bandwidth. Okay, so we have here your formula. What is our formula? So KTB, okay? So always remember the formula you have here. Your power is in terms of KTB. So this is 1.38 times 10 raised to negative 23. That is your Boltzmann's constant. So you have 400, but this is in terms of Celsius. So you have to add 273. Okay, so 400 plus 273 and then your bandwidth. So that will give you 9.29 femtowatts or raised to negative 15. Okay, so a pico is negative 12, negative 15 is femto. So we're expecting small values. Okay, so we don't want noise having large power. Because if that is the case, then your noise is greater than your actual signal is. And we don't want that. Okay? So, we are always expecting a smaller value of noise. Because if your noise is very, very large, then it will be very, very bad for your signal. Okay? So, how do you express this in terms of decibel? So, in terms of decibel now, okay, so in terms of decibels, this is given by your KTB or your 9.29 femtowatts. Since you are using dBm, that means automatically we're going to make use a reference value, an input, which is equivalent to 1 milliwatt. So in our denominator, we have 1 milliwatt here. So that is equivalent to negative 110.32 dBm. So imagine, your femtowatts is raised to negative 15. How many 0.00000 is that? Okay, but if we express that in terms of decibel, we just have a value which is equivalent to negative 110. Okay, so why negative? Why negative? Because your numerator in femto is lesser than your denominator. Okay, so we don't want a noise that has a positive value in dBm because that means it is greater than 1 milliwatt. And 1 milliwatt is very, very high already. Okay, so therefore, when your output is lesser than your input, so you expect a negative dBm. Okay? Because your 9.29 femtowatts is lesser than 1 milliwatt. That's why you have a negative value. Okay? So we have an additional question here. Determine the noise power in dBm if the temperature decreases to 100. So when it decreases to 100, since your noise power is directly proportional to the temperature, so what are we expecting? So since your temperature decreases, we are expecting a noise power which is also decreasing in value. Okay, so let's check for that. So we have here, okay, your PN now, your new PN is 1.38 times 10 raised to negative 23. Our new temperature is 100 plus 273 to make it Kelvin, okay, and then 1 megahertz. We will not be changing your your bandwidth. Okay, so it will not be changed. So we have here 5.15 femto. So as expected, it lowered down. Why? Because noise power is directly proportional to the temperature. So decreasing the temperature means we are decreasing your noise power. In terms of decibels, same step. Okay, so we have here 112.88. Okay, see, so from our earlier value, which is 9.29 to 5.15, but in terms of decibels, we only increased what, about 2 dBm. Okay, so the increase here is not very large, just 2 dBm. So it was decreased. Okay, since this is negative, the more negative you have, that means you decreased your value. Okay, and then finally determine the noise power in dBm if your bandwidth is doubled. Okay, so again, noise power is directly proportional with the bandwidth. So if we increase your bandwidth, if we doubled your bandwidth, so therefore we are also doubling your noise power. So what do we expect? So we are expecting a higher noise power here. So to continue, we have here your new noise voltage. Okay, so we will use your original temperature, okay, because it says here we're just checking the relationship between the power and the bandwidth. So we're going to stick with our original temperature, and then we have here you double your bandwidth. As you can see, we doubled your noise power. Okay, but even though we doubled your noise power in terms of decibel, we just increase it technically by 3 dB from the original 110 dB. So in comparing, you just change one parameter, okay, and then make use of the original value for the rest of the parameters. Just like in our letter B, we make use of the same bandwidth. We just change the temperature to get the relationship between the noise power and the temperature. Okay, and on the third example, letter C, we use the original temperature, and then we doubled the bandwidth to get the relationship between the bandwidth and the noise power. Okay, so as you can see, the formulas are very simple. So this is just direct to the point. Just direct substitution. So the formulas so far are very simple. Okay, so those are different types of uncorrelated noise. Okay, so what do we mean again by uncorrelated noise? When you don't have your signal, even though you don't have your signal, the signal may be present or not present. Those are the type of noises that your signals can encounter. Okay, so they are already there with or without the signal. Okay, so when you have an amplifier circuit, for example, even though you don't place an input coming from a signal generator yet, but those internal circuits are within the transistor itself. So once you use that transistor, automatically there is already a noise in that circuit, even without applying your input signal yet. Okay, so the second type of noise are your correlated noise. Okay, so what are those correlated noise? So correlated noise, these are noise that is mutually related to the signal and cannot be present in a circuit unless there is an input signal. Okay, so best example for correlated noise are harmonic distortions. Okay, so when unwanted harmonics of a signals are produced through nonlinear amplification. So we also use the term of amplitude distortion for this. Okay? So harmonics, they are integral multiples of the original input signal. Okay, so we have here degrees of harmonic distortion. We have the second order harmonic distortion. This is ratio of the RMS amplitude of the second harmonic frequency to the RMS amplitude of the fundamental frequency. Okay, so usually they are integral or multiples. Okay, so for example, if you have a fundamental frequency of 1 kilohertz, so you can have a second harmonic equivalent to 2 kilohertz, third harmonics equivalent to 3 kilohertz, fourth 4 kilohertz, and so on. Okay, although the amplitudes are decreasing, so the harmonics are infinite, but since their amplitude is very very small already, they become almost insignificant. Okay, so the total harmonic distortion, the combined RMS amplitude of the higher harmonics to the RMS amplitude of the fundamental frequency. So the percentage total harmonic distortion is equivalent to the voltage, RMS voltage of your higher voltage or higher harmonic divided by the fundamental frequency. Okay? So V higher is the quadratic sum of the RMS voltage of the different harmonics. For example, you have three harmonics. So what are their RMS value? We get the quadratic sum. So what do we mean by quadratic sum, class? So quadratic sum is you get the square root. So quadratic sum means the square root of your Vn 1 squared. For example, the second plus you have that's the third harmonic plus you have the third harmonic and so on. Okay, so you get the quadratic sum of the RMS voltage. And V fundamental is the RMS value of your fundamental frequency. Okay, the amplitude. Intermodulation distortion. So this is the generation of unwanted sum and difference frequencies when two or more signals are amplified in a nonlinear devices. Okay, so usually they form cross products. So when we discuss modulation, we can see the example of an intermodulation distortion. Okay, so for now, it's just the definition here. We have a plus and minus. Okay, so unwanted sum and difference. So originally, you have your fundamental frequency. For example, this is your original signal. We wanted to transmit this original signal, but all of a sudden, we created a signal plus a certain specific signal, and then we created a signal plus another or subtract another specific signal. Okay, so we produce cross products. We produce unwanted sum and differences in the frequency. So those are called intermodulation distortion. Okay? And impulse noise, this is characterized by a high amplitude peaks of short duration in a noise spectrum. So if you're going to look at a noise spectrum, for example, this is your example of noise like that. So usually that noise is small and then all of a sudden you have a higher peak of like that. So this higher peak here is what we call an impulse. Okay, so just a high peak value in a short duration of time. So in the total noise spectrum. Okay, so sometimes we eliminate that using clippers. Okay, and then we have interference. Okay, so we will be hearing a lot of interference. So when information signals from one source produce frequencies that fall outside their allocated bandwidth and interfere with information signals from another source. So maybe you have experienced that you're listening to a certain radio station, for example, and then upon passing a certain area, okay, so upon passing a certain area, you have while you are listening a certain voice or a certain DJ coming from other station interfered with what you are listening, for example. So that is what we call an interference. Or you're talking with somebody on the phone and then suddenly there's an airplane or some and then the frequency from there interfered with your conversation, so you can hear an interfering sound. So that is what we call a noise, and that is in the form of an interference. Okay, so those are the different types of correlated noises. Okay, so we have here miscellaneous noise. We have flicker. Okay, so what do we mean by flicker? So at low frequencies, a poorly understood from noise is found in transistors. Okay, so there's a flicker. So this is also known as modulation noise. This is inversely proportional to the frequency. Thus, this can be completely ignored above 500 hertz. Okay? So, noise in mixers, nonlinear amplifier circuits are much noisier than amplifier using identical device. Okay, so addition of noise due to several sources, assuming two sources of thermal agitation noise generators are in series, we just get their sum, square of their sum, and then we get the square root. So this is how you get the since those noise are in forms of RMS, we do not just add them like what we use in DC voltages. Okay, so we make use of this formula when adding noise due to several sources. Okay, so a while ago, we have discussed the signal-to-noise ratio, okay, in the bandwidth topic. So this is your signal-to-noise power ratio. Okay, so the ratio of the signal power level to the noise power level. So SN is your signal power in terms of watts, and then signal noise power in terms of watts also. So in this case, your signal to noise power is unitless or absolute ratio because your watts will be cancelled. But, okay, we can express your signal to noise in decibel. So, since we are talking about power ratio here, we make use of 10 logarithm to the base 10 of your signal to noise power ratio, or PS all over PN, or your absolute noise power. Okay? And then we have here a noise factor. So, noise factor is in terms of F. This is the ratio of the input signal to noise power ratio to the output signal to noise power ratio. Okay? So, F is equal to the input signal to noise. So, you have a transmitter, you have a receiver, for example. You have an input side, you have an output side. Okay? So, there's a possibility that you have a noise in the input. Okay? And then, after eliminating through the circuit, for example, you have filters already, and at the output, you can also have a signal to noise power ratio. Okay? So, the noise factor is just a ratio of these two ratios. Okay, so the input signal to noise and then the output signal to noise. Okay, so the input power and the output power and the noise power in the transmitter, and then the input power and the output and the noise power at the receiver side. Okay, this is also absolute power ratio, so therefore it is unitless. But if we wanted to express this in decibels, we call it now noise figure. Okay? So, noise factor expressed in decibel is what we call noise figure. So, noise factor stated in decibel. And that is 10 logarithm of F. We have your equivalent noise temperature, or TE. So this is hypothetical value that cannot be directly measured. So you cannot use a thermometer to measure this. Okay, so we cannot get a thermometer and then measure the equivalent noise temperature. Okay, so all you have to do is to compute for this. As long as we have your noise factor. Okay, so temperature, equivalent noise temperature in terms of Kelvin is equivalent to T, that is the environmental temperature. Usually make use of the reference value of 290 K. So if it is not given, we're going to make use of 290 Kelvin. But if it is given, we're going to make use of the value that is given to you. Okay? And then you have here your noise factor. Okay? So F minus 1. So your noise factor, this F here is the absolute ratio and not in terms of decibels. Okay? So, T, temperature, if it is not given but the noise power is given, we can solve for that using your original formula earlier. Okay? Wherein the noise power is equivalent to KTB. So, this time, your temperature, environmental temperature is given by the noise power, okay, divided by the the Boltzmann's constant multiplied by the bandwidth. Okay? So you have a set work. You have a set work here. So there is a drop box. I will be providing a drop box in the school book wherein you can submit your set work. Okay, so that's the end of our discussion. Okay, so thank you and have a nice day.